Now let us understand buffers. Buffers are the solutions which resist the change in their pH even on addition of a small acid or a small base doesn't let the concentration or the pH to be changed. So the solutions which resists change in the pH even addition of small amount of acid or a base are called buffers, which resists change in their pH. They doesn't let the pH of their solution to be changed even if you add the acid or a base. That means the addition of the acid, which we believe that will decrease the pH, or of an addition of a base which will increase the pH, doesn't let the pH to be changed. They can resist the addition of an acid or a base, and even on their addition, the pH is never let down to be changed. They can never allow the change of the pH in their solutions. The reason is their mixture is such that they can consume whatever the H ions and the OH ions are added, and they never let the change in the H ions and the OH ions concentration happen. If it goes beyond a certain limit, then only it gets changed. Otherwise, the addition of a small acid or a small amount of a base is not actually will be affecting the pH of these solutions. Such type of solutions are called buffers. Buffers are very important solutions. They are used in maintaining the pH of the blood the moment it is taken out for the dialysis. They are used in maintaining the pH of the other substances, solutions, and they are very important for not only for industrial as well as for the biological purposes. Generally, whatever the types we study, we classify them, the buffers, into two major categories. Buffers are of two types. Acidic buffers, basic buffers. Let us first do acidic buffers. Acidic buffers are mixture of weak acid and its salt with strong base. So, let us take an example. Weak acid, acetic acid, and its salt with strong base is your sodium acetate. The mixture of these two forms a buffer. Definitely when these two are mixed, since it's an acid, the medium will be acidic, and they at and around a pH of 4.75, they forms a buffer solution, which even if the small amount of acid or a base is added, will not allow the pH to be changed. So this is an example of your acidic buffer. How they behave is, how they show their buffer action is, let me explain it to you. You have to first understand how they show their buffer action. Now let us understand the buffer action of this acidic buffer, which is a combination of a weak acid and its salt, which forms an acidic buffer at around a pH of 4.75. See, the moment we take this salt, sodium acetate, I told you that all our salts which are taken are strong as salts, dissociates completely. This dissociates completely in water, forming acetate ion and sodium ion. Now, in its presence, when this weak acid is taken, we know that it won't be dissociating completely. It will be forming acetate and NH plus ion. Now, due to common ion effect, due to high concentration of this acetate which is already generated from this salt, this acetate ions concentration will become large. This will make this acid to go back. So the dissociation of this acetic acid is taking place in a very, very small amount. Now, what is the buffer action is? If acid is added, once this if acid is added, we are adding the H plus ions. Who is there to accept this H plus ions? Remember, this acetate ion which is from this salt will combine and will form acetic acid and will not allow this acid to dissociate back. So what will happen is, whatever the small amount of the acid is added or the H plus ion is added, immediately gets consumed by these acetate ions forming acetic acid, and since there is no net change in the H ions concentration, this is not going to change the pH. So this is how it can consume H ions, acids, and will not allow the change in the pH. Okay, now let us find out how the base is added and how it is actually consumed. If base is added, the OH minus ions introduced will immediately combine with the H plus ions which are actually obtained from the acetic acid, and they will neutralize each other forming water. But as I have told you that the concentration of these H plus ions will be very less due to the suppression of the dissociation of weak acid by common ion effect. But we know from the Lee-Chatter's principle, the more the H plus ions gets consumed, the more the degree of the dissociation of the acetic acid will increase. It will dissociate to the larger extent, giving you more of the H plus ions. So in this way, if the base is even added, it will be continuously being consumed by these H plus ions forming water, and therefore no net change in the OH ions concentration, and therefore it can resist the change in the pH and will not allow the change in any change in the OH ions concentration. Basic buffer is a mixture of weak base and its salt with strong acid. So let me take the example of weak base like ammonium hydroxide, and its salt with strong acid like HCl will be your ammonium chloride. So the mixture of these two acts as a basic buffer, and they together at around a pH of 9.25 forms a basic buffer. The basic buffer, in a very similar way as we have seen in case of an acidic buffer, will be resisting the change in its pH by consuming whatever the H plus ions or OH minus ions it has been added, and never allows that pH to be changed, which is actually called its buffer action, because the ammonium ions will consume the OH ions, and the H ions given out, OH ions given out by this will consume the H ions, will never allow the change in the pH. So these are your buffers, basic buffer, since it's a base which when added or when these two are mixed will make the medium become basic, and that is why around the pH of 9.25 they forms a basic buffer.